Welcome everyone to this guest lecture by Magnus Myreen. So today he will teach us about HOL, and Magnus has been working with theorem provers for a very long time. He's an expert in HOL in general, and he's one of the persons responsible for working on the CakeML project. So I'm very excited to have Magnus here, and welcome.
Thank you. Okay, so yeah, as you can see, this is a guest lecture in your course on interactive theorem proving with dependent types. And when I got this invitation, I was a bit surprised because HOL is an interactive theorem prover, but HOL provers do not have dependent types. And well, it's good to also know HOL provers if you know dependent types. Style provers. And why is that? Why would you why does it make sense to learn about HOL? Well, here's one reason. Both Apple and AWS have independently started ambitious projects on verification of low-level systems code, and both chose Isabelle HOL. These started, as far as I know, from scratch, so it's not like they needed to be compatible with old code. So then you can ask, why did they choose Coq? Why didn't they choose Coq, Lean, or Agda? And so this is a motivation to learn about HOL, because clearly they must have done some weighing up and chose HOL instead. So by the way, I don't know why they chose one or the other. I'm not associated or inside either of those companies, but I can make some guesses. Okay. So this is the outline of the lecture. I'll talk first about the history of the HOL ITPs. Then I'll talk about my work within the HOL ITPs, and then I'll end with sort of a more, well, some demos and some closer look at what HOL looks like really when you use it, and sort of corner cases that might surprise people who come from Coq. Okay, so history of HOL ITPs. So I'll start with just sort of motivation, but go through it quite quickly. This is motivation for interactive theorem provers in general. Where's my cursor? Oh. Okay, so suppose we have this question. How can I know my software satisfies a spec? Well, of course, you can prove that it satisfies a spec. How do I know my proof isn't flawed? Because, of course, proofs about complicated programs tend to be very complicated themselves. By strictly following the rules of a formal logic, you can be sure the proof is sound. Okay, good. Well then, what is a formal logic and how can I be sure to follow its rules? Well, answer is a formal logic is a formal system with limited vocabulary and exact syntactic rules for deducing new facts from other facts in the system. Okay, and you can be sure to follow its rules if you use software called interactive theorem provers to create and check your proofs. Then a critical mind might say, wait, how can I trust the correctness of these ITPs, interactive theorem provers? The answer there is usually ITPs are very defensively programmed. So we try to program them in such a way that bugs should, or at least soundness critical bugs, should hardly exist or should not exist. Okay, so I promised some history. So in the late 1960s and early 1970s, there were these three significant ITPs were emerging. So Automath is the first practical system that could be used that used the Curry-Howard correspondence, which you must be familiar with from Coq. Then there was also the Boyer-Moore theorem prover, which nowadays is called ACL2, or its modern version is called ACL2. So in this prover, it's very different. It starts with a programming language. In that case, in its case, it's Lisp, and uses it as a logic. So they adjusted it a bit so that it fits an understanding as a logic. It has a very strong emphasis on using rewriting in the form of a simplifier, which is conditional rewriting and so forth. So it was very ahead of its time with that. And it has automatic induction and all sorts of cleverness. So it tries to be very automatic, although it is still considered an interactive theorem prover because the user does guide it in a certain sense. And then the third significant one is LCF by Robin Milner, and that's LCF stands for Logic of Computable Functions. The logic itself was by Dana Scott, but the prover was by Robin Milner's team. So I will focus in on LCF because that's the ancestry to the HOL provers. So it started off with Stanford LCF when Robin Milner was there. So it was Robin Milner and Whitfield Diffie, who later became very famous for cryptography, but he started off working actually on LCF. Diffie taught Milner Lisp, and the original LCF was implemented in Lisp. So key features of this early ITP was that it has a goal manager, so that you can do proofs in a goal-oriented fashion, and it has had a powerful simplifier similar to ACL2. The Boyer-Moore theorem prover, sure, inspired, I'm sure, by them. So it had some major shortcomings. The size of proofs was limited by memory, because you prove something, you keep the proof around, but in those days memory was very limited, so your proofs got limited too. And it had a fixed set of proof commands, which was also limiting for the sort of a power user. So Milner moved to Edinburgh, where he started Edinburgh LCF. And there he worked with Lockwood Morris and Malcolm Newey, and Milner tackled the shortcomings 1 and 2. And in particular, he decided that the system should only remember results of proofs. It shouldn't remember the proofs themselves. And the user should be able to program new tactics. So it's no longer the case that you should trust the entire source code somehow. You need to be able to allow the programmer to just write tactics in some language, in a programming language. Okay, so he had a key idea, and this is it. So especially for number one, addressing number one, we introduce an abstract data type called Theorem or Thumb, and it consists of the predefined values were axioms of the logic, and then there are functions over the Thumb type that implement their inference rules of the logic. So you have theorems that functions that, given a theorem, will produce, or given one or more theorems, will produce another theorem. And so if you only start from the axioms, and each of these theorem producing functions are sound by the inference rules of the logic, then you can only derive provable facts. But you have not kept the proofs. You have just sort of, through keeping it around, through this theorem type, have you sort of tagged every proved statement. And of course, for this theorem stuff to work at all, you have to have strict type checking that ensures that all values of type theorem really follow from the axioms or the inference rules. So that was the idea of Edinburgh LCF, and that is why all HOL provers are nowadays called LCF style, because they kept this idea. And these ideas resulted in a new programming language called ML. Okay, which stands for meta language, because it is the language you are manipulating, the object language. The object language being, in this case, LCF, the logic of computable functions. Well, in 1975, Morris and Newey moved away, and Chris Wadforth and Mike Gordon joined the effort. Mike Gordon, by the way, was my PhD supervisor, and they wrote the first paper on the ML programming language, which is a meta language for interactive proof in LCF. That was a Popple paper long ago. And then came Cambridge LCF, where Mike Gordon and Milner moved to Cambridge, but I think Mike first. And then Larry Paulson, you might have heard of him. So he started as a postdoc for Mike Gordon in the early 1980s. And here is a picture of him. And then Larry and Gerard Huet produced an ML compiler that sped up LCF by a lot. And by the way, Gerard Huet is behind the Camel. He started Camel. Okay. Yes. And Larry worked on Cambridge LCF. But then at the same time, Mike Gordon started the HOL Theorem Prover. So Mike was doing hardware verification in LCF, and LCF was very much had foundations that that are in domain theory, which are complete overkill to hardware verification and made life complicated in his work. So he was looking for something simpler. And then a postdoc showed Mike how hardware descriptions could be encoded nicely in higher order logic, so HOL. And then so what is HOL? HOL is Church's simple type theory extended with polymorphic types. That is what higher order logic is. It's just lambda calculus with a simple type theory on top. And you can use it for doing, it is a logic, so you can do all sorts of things in it. And then, so Mike cloned Cambridge LCF and adjusted the theorem type to implement HOL instead of LCF. And that's how the first HOL prover came to be. And since then, there's been HOL 88, HOL 90, HOL 4. HOL 4 means sort of the fourth version of the main strand of HOL provers. There's also proof power, there's Isabelle HOL, and there's HOL Light. There seems to be some questions. As in system F or something different. I missed which that is referring to. It's polymorphism. I can show you later, but there's no binding of type. There's no binding of type variable. It's top-level polymorphism. It's the type system is very simple. As the name suggests, simple type theory. You'll see. Actually, the simple type theory originally didn't even have polymorphic types, so it was really, really simple. Okay, are there any other questions at this point? This is sort of the history part done.
I can also just say, you commented in the beginning, the course is about dependent typed and interactive theorem proving. But I think that the point of this kind of guest lecture is to widen a little bit the perspective of theorem proving. So that's the great thing about this. Yeah.
So I'll talk about my work in the HOL Theorem Prover, and because I put it here because it sort of attaches to the history in some sense. You'll see. So prior to my PhD, Mike hired Anthony Fox as a postdoc, and Anthony continued Mike's hardware verification. And there was an ambitious project to prove the functional correctness of an ARM processor down to the RTL level. Sort of looking back, currently, maybe this doesn't seem as a very ambitious project, but at the time, some 20 years ago, that was actually very much pushing what could be done. So this was an ARM RTL design that was in the public domain. So even at the time, it was a little bit outdated, but it was to show that this can be done. So a byproduct of this is that there was an extensive definition of how ARM machine instruction executes. So machine code executes. So that's the ISA specification, instruction set architecture specification. And so there was this question, can Anthony's ARM model be used for actual proofs about machine code? Because it's very exact, but it's also very detailed. can it be somehow used? And my work started with this kind of stuff. Anthony had tools that could, for instance, here's a very simple instruction. It's the add R, so add the value of register 0 to register 0 and store the value in register 0. If you gave this to his proof automation, it could produce this kind of summary. So if you read memory from this the program counter in this state, if you read memory in that state, if you get that out and your state was well defined to start with, and by the way, this hex here is the encoding of that instruction, then you see that the next ARM instruction, next state from according to ARM from this state is that the program counter is updated with +4 from its original value, and register 0 gets the value of register 0 plus its value register 0. So that's the kind of awful mess one got out of the ARM model. This is a particularly neat one because it's such a simple instruction, but there are some much more complicated ones. So I developed a bunch of infrastructure. First, one of these, a HOL logic that fits on top of these. And initially I only had ARM, but then I also extended it to x86 and PowerPC to show that it's portable. And then I built some proof automation. And proof automation is something that's quite, I wouldn't say easy, but it's quite pleasant to develop in a HOL prover, because you sit in, you're constantly in a real programming language. So I developed a tool that can use the HOL logic automatically. And the tool does this. If you give it some machine code, you gave it to this proof producing decompiler, it produces a function as a functional program that sort of represents what the code computes. And it gives a theorem also that relates the function to the original code in terms of portrait. And then I built on top of this a proof-producing compiler that sort of flips the decompiler. So given a function, it just invents some code that it thinks does that. And then it uses the decompiler to actually get the same function out. And then, so it proves correspondence between the input you gave and the decompiler's output. And then it can produce code. So the compiler works like this. You give it a function that looks like something the decompiler could produce. The compiler produces code for which that really has that behavior and a theorem connecting the function to the code. Anyway, this is a bunch of proofs of automation on top of the HOL triples. And this is what it looks like, the decompiler illustrated on an actual example. So here we have the machine code. This is assembly code just for readability. You don't need to read it right now, but I will show you, I'll read it through when I go through here, what's below. So the decompiler produces a readable HOL Four function, and it produces really two functions here. The first one is the description of the entire block of code, and one should read it as follows. Suppose we get input register 0, the value of register 0 is R0, R1 is value of register R1, and then we have memory modeled by M. First thing the code does in this instruction is to move 0 into R0. Okay, so then in the output, it becomes a let expression. And then it calls G, which is this loop. You see there's a loop between these. What does the loop do? Well, it first does a comparison with R0, register 1 with 0. That's what it does here. And then if it turns out to be equal, all of these are not executed because they have this conditional suffix here. So not equal. So if they are equal, then you just return. You sort of plop down here and you continue executing from here. So that's why this function G just returns. If not, then you go into the else branch and you add 1 to R0. That's the add. Then you load memory from R1 into R1. and that's this line. And then here in the machine code or assembly, you can see that the loop starts again, and that's what it does. It jumps up here. And by the way, this computes the length of a linked list. And there's an interesting case that what happens if the linked list is cyclic? This doesn't terminate, and that's actually fine. It's fine to define a non-terminating function in HOL as long as it is tail recursive. And I can get to that at the end of the lecture if you're curious how that can work. But it can. In HOL it can. And what you also get, as I said, the decompiler is proof producing. So what you get is a HOL triple, a precondition, the code, and a postcondition. And there's also a pure precondition here, which says, well, if it terminates, if f terminates for these input, then this HOL triple describes the code. So it says, if the program counter p points at the start of the code, then, and the registers are actually represented like this, then what we have is that f describes the output state of R0, R1, and M. And the program counter now points at the byte address immediately after these instructions. So, yeah, so then I realized that one can do a bunch of abstraction, and one can teach this compiler at the top about Lisp primitives if one, yeah, I don't have time here to go into how it does that, but basically I could make these functions, these, here they're about 32-bit words, but by teaching the decompiler certain HOL triples about instructions, I can make it talk about Lisp Lisp operations over S expressions. So I can do car and coulter and cons and all that Lisp stuff. So then I could produce, then I had a compiler for Lisp. And that was sort of the end of my thesis. I could show that I had a Lisp interpreter, verified Lisp interpreter that is verified down to the machine code for ARM, x86, and PowerPC, and of course the tooling that got it there, and including a garbage collector and all that. Okay, so here's what I really learned from my PhD, sort of a reusable lesson, is that developing custom automation and mixing that with interactive proving leads to high quality results quickly and a lot of fun. So that was what I learned. And I think the whole theorem prover is particularly well adapted for, it really encourages or is a good place to do custom proof automation. So that's what I learned. Okay. So, and then what did I do? I went out into the world after my PhD, and I worked on the HCL4 operating system with the L4 verified team in Australia, and they had done this this verification, which stopped. Well, it has at the top level a high level design, and then a low level design. They proved those corresponding, and then or refinement between them. And then they had a detailed model of the C code that was extracted from real C code. And then they proved those corresponding. But what they didn't have at the time is they didn't have any formal connection to the ARM machine code that is generated from the C code. And so in a collaboration with me, between me and them, we put in the Cambridge ARM model underneath, and then we used my decompiler to get up to a sort of intermediate point there. And then Thomas Sewell did a PhD on doing this refinement proof, mostly automatically. And that was how my tooling got used by others. And yeah, so SCL4, the operating system verification, the top half of this picture got the ACM Software Systems Award last year. Okay. Yeah, that's Thomas Sewell's PhD. Okay, so another break for questions. I can also flip back in the slides if you want to ask questions. Just ask on.
So maybe you will come to this. I can just ask Magnus.
Yeah.
When it comes to proving things like, say, that you want to prove type safety or something, you have a formal semantics and you want to do type safety proofs. That is what we are using, for example, in this course, using COC for. How is HOL and HOL Four doing that kind of proofs, which is a little bit different from what you're showing right now?
Yeah, that's a standard sort of interactive proof also in HOL Four. Maybe you write some tactics here and there to help you with some sort of common cases. Usually common cases one would try to package up into lemmas instead of, but I think that kind of proof will be very similar in COC, I would say.
All right. But there is also, a large set of tactics that you can in libraries that you can reuse and so on in HOL Four in the same way.
Absolutely, absolutely.
Yeah.
I'll get to towards the end. I'll have a demo where I show a proof in HOL Four, and then you'll see that maybe it's a little bit different from COC in some ways. Okay, well then I'll move on from the green slide. Okay, so I just want to say that I've always been impressed with the Boyer-Moore prover, or ACL2 as it nowadays is called. And after my PhD, I had this this opportunity to talk to work with Jared Davis, who used to be who was Moore's PhD student. So he sent me an email where he asked, "Can I try running Milawa on your verified Lisp interpreter?" And this was quite a roller coaster ride. So I just want to say that Milawa was a really cool, or is a really cool, theorem prover concept, because in the LCF style approach that I described earlier, with Milner's approach, is that you have a little core of code that implements the logic and has this theorem type. And the idea is then that to make it an actually nice system to use, you write a bunch of code on top of it that then implement a rewrite or a decision procedure or a simplifier or first order logic prover or SAT, SMTs or connections. You write a lot of custom tooling on top, but then there's this problem that you never get larger steps. So you always, all of the reasoning always goes down to the primitive inferences. So if you do a rewrite, sometimes a number of primitive inferences, it can be hundreds or thousands, depends on how deeply in your term you are. But this is ACL2, and the Boyer-Moore theorem provers don't have this problem. But they also don't have a small trusted kernel. Instead, the Boyer-Moore prover, you have to trust the soundness of the entire system, which is rather concerning if you come from the LCF tradition. So the Milawa approach had a very cool way of doing it. So the Milawa proofs, it also has a little kernel that you have to trust. And all proofs must pass this core. But the core can be replaced by a new one at runtime. That's a bit weird, right? How can you do that? Well, by proving that the new core is sound with respect to the original one. So this is a very reflective style. So what you do is you do some derived rules. This is now, so yeah, well, oops, sorry. So this derived rules is a new kernel that can do things, sort of fuses multiple operations so that you can do them faster in fewer steps. And then what you do is to be able to switch to the derived rules blob being the new kernel, the new proof checker at the heart of the theorem prover, you have to prove using the current core that this one is sound, or every proof you can do here, you can also do there somehow. So that's, and then you can, from then onwards, you can do a switch command, and now this is your new kernel. Okay, And then you do this many times until you have very powerful auto tactics that just sort of do automatic proofs in one step. So this is, I was blown away by this and very inspired by Milawa. So I tried to work really hard with Jared Davis. And we managed to do it. So we built this stack where I built a new verified Lisp, which is 7,000 lines of x86, and it's proved correct with respect to x86 semantics. And on top of that, we have the Lisp semantics, so that this Lisp implementation implements. And then the kernel of Milawa theorem prover was proved sound with respect to that on the bottom end, and at the top end, it's the semantics of the Milawa logic that is essentially a simplified version of the ACL2 or Boyer-Moore provers logic. So I know that quite intimately. And these 2,000 lines of Milawa Lisp includes the reflection mechanism, of course, because we need to make sure that it's sound however the user runs the switch command, which is quite exciting. Okay, and then, so in my mind at least, this Milawa, a Lisp for Milawa, was a precursor to the CakeML project. The CakeML project is now, it's just a name, CakeML, but it originally meant Cambridge and Kent ML, because ML variants are usually named after places. And at the time, the original developers were at Cambridge and Kent. So this has produced a significant verified compiler for ML, and I've been part of it since the beginning. And this then is the major result there. It's a POPL paper in 2014, 36 years after the original ML paper, and it's received this year the most influential POPL paper award. So, and what's new, what's sort of most significant here in terms of verified compilation is that it is the first, does it say here? Oh, it's a bit off the slide, but is the first verified compiler to be bootstrapped within the logic. That was a first here. Okay, and let's see. And then coming back to sort of the whole tradition, and so Milawa, I proved the Lisp, Jared Davis Lisp implementation of his prover correct. So here in the CakeML project, we proved John Harrison's HOL Light theorem prover correct. Sound, I mean. And this is really meant to be a clone of the original HOL Light, the verified clone. It really feels like HOL Light when you use it. It has the same read-eval print loop, which is all verified and uses dynamic compilation and so forth. Yes. Okay, so now if we go back to the motivation, which I started with, remember we said there was this, wait, how can I trust the correctness of these ITPs? Well, I said ITPs are very defensively programmed. And now we can say some are even proved to be sound, because that's what this candle prover is. It's a proved to be sound version of HOL Light. Proved with an unverified ITP? Well, yes, that is true. It was proved using HOL Four, which is unverified. So yes, we are using that. But still, we are making progress, I believe. Because if you, for instance, look at this paper by John Regere's group, he tried to fuzz test the CompCert verified compiler, and he couldn't find any bugs, even though he found tons of bugs in all unverified C compilers. So even if you don't really believe that CompCert got exactly the C semantics that everyone thinks C semantics is, possibly there's some disagreement there, I'm not sure. But even so, it seems to be, if you come from a completely empirical point of view, it's very hard. You can't poke holes in these things. Okay, so now I'm on to the last part. which is meant to be quite flexible and sort of open-ended. I'll take a closer look at HOL 4, which is the variant of HOL I use, and with demos. But before we go to demos, I just want to recap one thing. What is the trust story for Coq? As I understand it, proving produces proof terms or proof object. I don't know the terminology. So that are checked by a trusted proof checker. And so when you use Coq, all you really need to trust is the proof checker. While in HOL provers, they follow the LCF style. So proving produces values of type theorem using a trusted LCF style kernel. And one benefit I want to point out with this is that proofs are not kept around. Proofs don't occupy any space. We only can keep around the conclusion of the proof. And we don't keep that around either once it's no longer reachable in your program. So, I mean, it's garbage collected like any other value in ML or OCaml if you're using HOL Light. So you might say, oh, well, this doesn't matter anymore. When LCF was designed, in the 70s, memory was very limited. But nowadays, we have tons of memory. Well, you're right to some extent, but also, if you then look at the HOL provers, how many inference rules they actually produce, it's easily millions for even fairly simple proofs. So if you were to actually keep track of all that, I think it's a bottleneck. And I think the Isabelle HOL prover does have a mode where it keeps track of proof objects, but everyone turns it off because it slows down the prover. Yeah. Okay, so that's the trust story. And then I want to point out that the HOL logic is really simple. And this I want to show by going to look at the HOL Light sources. I hope you can see this okay. So this is the LCF kernel at the heart of HOL Light. And you can see it is only, it depends on which line count you want to read. It's 548 lines of code of OCaml. Oh, okay. There's a question. How about the similarities between HOL and Isabelle HOL? So Isabelle HOL is wait. There's a difference. So Isabelle minus the HOL at the end. Yeah, I'll share the link. Just a moment. I'll copy it into the chat. So Isabelle HOL, or rather, Isabelle is a framework for implementing theorem provers. And Isabelle HOL, so Isabelle/HOL, is the instantiation of Isabelle to the HOL logic. There's also Isabelle ZF for set theory, and there's a few other minor ones. But Isabelle HOL is, when people say they use Isabelle, they 99% of the time mean they use Isabelle HOL. So that's the difference. Isabelle also tweaks the HOL logic a little bit. They add ad hoc overloading in a way that the other HOLs don't have. So that's the difference between the other HOL prover, HOL Four, HOL Light, and so forth, and Isabelle HOL. I hope that's. Then on top of that, they have added type classes and locales and things. But I think most of those are actually not changes to the logic. They're just more implementation. Okay, so I want to show you the HOL Light kernel, just to show you how simple this logic really is. So here we see, well, this is the signature of the kernel, so it goes on a bit. Those are the functions. But here is the data types involved. So a type in HOL Light is either a type variable. Oh, this is not good. It's being too smart, or I'm being too dumb. Okay, so we have this It's either a type var or an application of a type constructor to a bunch of HOL types. There's no quantification, nothing like that. Types are really simple. And then, so there's no local names here. Then we have terms, which are a variable, and a variable consists of a string and a type. That's all. And a constant is a string and a type. And this then, the meaning of this will depend on what, you know, it's a fixed thing. You can't rename this, for instance. It's a constant. And then you have combination, which is function application. So you apply this. This is the function, and that's the term it's applied to. And then we have abstractions, which here the type is a bit misleading because this must be a variable, actually. So this is just a variable, and this is then the body of the abstraction. So this is lambda. And what is then a theorem? Well, a theorem is just a sequence of term list and term. So these are the assumptions, and that's the conclusion. Okay. So, and if we look at the signature, it leaves the theorem type abstract. It doesn't, you can't from outside do anything with it. While the other two are private, which means that you can pattern match on them, but you can't create them outside the kernel. So that's why, so these are all protected by the kernel. They can only be created by the kernel. Okay, and then it's just normal OCaml programming, the rest, and they're not that exciting. There's a bunch of things, destroy type. Yeah, what should I say? My point is here that this is not hard, and this is not very complicated code. Like is var, well, if it's a variable, yeah, true, otherwise it's false, and so forth. Most interesting one I know, I think, is type instantiation, which this might, yes, this is it, type instantiation, because it's recursive in a funny way. Yes, because it has to, when you instantiate a type, you might accidentally cause a variable capture with a bound variable of the same name, which might then become of the same type. And so you have to keep clashes around. You raise the clash and you catch it here and you deal with it. And yeah. So, and there's a few definition mechanisms here. Where is it? Yeah, there's new basic type definition, which requires the term you want to define to be an equality and a name, and then a right-hand side, and then it checks a bunch of things and adds it to the definitions reference. Okay, there's a question. Well, let's see. I saw no polymorphism in the types, in the type or terms. Where does type instantiation happen? What do you mean? There is polymorphism. That's a type variable. That is what gets instantiated. And if you do term instantiation, then you're instantiating this. Here is HOL Light opted for explicit names, which causes a bit more work with substitution and instantiation, of course, but otherwise gives a very clean presentation. Yeah, so I thought as a demo, I'll use something from my from lectures I give on compiler verification. This is a toy compiler. So the syntax will compile is just consists of literal numbers, natural numbers, and variables and expressions plus, which can then take two expressions. Okay, so it's a very simple compiler, and we go to a target toy machine code that has this shape. So it has three instructions. You can move a constant into a named register, or you can move the value of a named register into another one, or you can add two named registers and store their result in another one. Okay, so, and you should understand it as a target program consists of a list of instructions. So we use a big steps relational semantics to define the evaluation of the source rules, the source code. So here I've written in a kind of weird way, but anyway, this is not, you should almost read it as English rather than something mathsy. So in an environment, variable S evaluates to value V if you can look up S in the environment and find value V. Then there's also a constant doesn't depend on the environment at all. It always evaluates immediately to the value that it's holding. And the most interesting rule is, of course, the recursive one, which is the plus. So if you have plus x1, x2 in some environment, if you want to evaluate it, then you have to evaluate successfully x1 to a value v1 and x2 to a value v2, the same environment. And the result of the plus will be v1 plus v2. And this is just natural number plus. So it's, I hope it doesn't come with any surprises, these definitions. If they are, then say something on the chat. Yes, this is a big step because it describes the complete evaluation. And then the target semantics is written in small step style. And here, it's a state is a mapping from names to values. And so we have a step function that, given an instruction and a state, gives you the next state. And here, there's no such thing as failing. It always just works. So when you run a constant instruction, it updates state so that the mapping is updated so that S points, gives the key S now points to the value N. The move instruction is very similar. We update the state such that S1 points at the value of looking up S2 in the state. And we can also, the add is just a generalization of that. Instead of taking just the value of 1, we take the value of 2 and do addition on it. And if we have multiple steps, if we want to execute an entire target program, which is a list, then if it's an empty list, then the initial state is already the final state. Otherwise, there's a cons in the list of instructions. We evaluate the first one to get the state after the first, and then we do the rest of the instructions by recursion. So this is the target semantics, and the compiler function will verify. Oh, there's a bunch of there's a long comment. Is there a special reason to have the target language in a small step semantics and the source language in a big step semantics? It's generally the case that, well, let's say it this way. One can choose both. You could choose either way in both cases. I think it's slightly more sensible to have the target semantics in a small step semantics in general, because if you have unstructured assembly, that has less structure, so it's easier to do just one step. While high-level languages that have a lot of structure sort of naturally fit into big step style. That's my opinion, at least. And then, of course, once you have concurrency and things like that, big step style is not so convenient anymore, and you probably want a small step semantic. But here we are using is it making the proof easier? I don't think it matters. The source big step semantics phrasing does matter because it affects how we do the induction in the proof. Yeah, so there it matters. Could it be done there? I think doing a small step would have been a little bit more work. in the proof. Yeah. In general, I think big step semantics is nicer in compiler. Compiler verification, if it works. As I said, once you have concurrency, I don't think it works. Okay, so this is the compiler function we'll verify. The contract is this, that given an expression to compile in the first argument, the compiler will generate some code such that it stores the result in register n. And registers now, I call them name in the previous, but name is just a synonym for natural numbers as well. So it's obvious how to compile this. The constant k, we just turn it into the constant instruction that takes the constant and plugs it into n, the register n. A variable, now this one produces a move of, it looks up the content of register v and puts it into register n. And this also shows another convention I'm using here now, that variable names in the source correspond to register names in the target below n. Okay, and then plus is very simple to compile. We first, so plus x1, x2, we first compile, take the code that compilation produces for x1, and then we append the code for x2, and then we append an add instruction. And we set the target registers like this. So x1, the value of x1 will at runtime be eventually at the end of this code snippet live in register n, while this one will put this value in n+1. And so the add instruction can just do n and n+1 and put that into n, which is there. Susceptible to clobbering. There's a question. Yes, it is susceptible to clobbering. We need to make sure that n is larger than any variable. And that comes out in the compiler proof, that we have to have that n is sufficiently large. Yep, that's it. So this is the compiler. And now how about, oh yeah, yes. So there's another question or comment in this in the chat, which says, also compile never overrides something less than n except for variables, right? Indeed, that is correct. Compile, when you have n+1 here, leaves everything under this unchanged always. Indeed, that is something we have to prove as part of the proof. Yeah, that's very accurate. Good. So here's the correctness statement. We will prove, but I thought I'll show it in HOL in a moment, but I wanted to just show it here first because it's a little bit easier to point and explain. So first of all, we say for any expression, any environment, any result, and then for which the source semantics can produce. So whatever is accepted by the source semantics, we will know the following. We will know that from any state and any k, and what are these states? State is what goes into the steps function. Remember, the steps function is the target semantics, operational semantics. It's given the state, so state is the initial state, and compile and k is the where the result should go. We have an assumption, which I'll get to in a moment, but what you should see is that I'm taking this result and putting it to state prime and checking that, yes, at variable k or register k, we have res, which is that. So it has correctly, so the code that compile produced, when you execute it, produces the same result as the operational semantics here, the source semantics. The target semantics has produced res in k, and that matches the source semantics. So let's see, I have some for every evaluation of the source for target state and case such that, okay, yeah. So now let's look at the assumption I have here. It says, for anything I can look up in the environment, then it must be the case that the state I have, when I look at that name in the environment, I get the value that I found in the environment. And the name you used for the variable must be less than k. Okay, so that's just sort of setting this k sufficiently high so that it doesn't interfere with a variable we might read. One could relax this a little bit and say, we only actually care about this for variables that appear in X. So one could put that as an assumption here too, which makes the entire assumption line weaker, which might be good, but this is good enough to show. And then there's so this is really what we want to know. I would say the result will be, res will be stored at location A in the target. And then there's a separate, the last line states what was mentioned on the chat, that indeed the state is unchanged for any value less than k. So k was the target location for the compiler. So anything less than that stays unchanged. And that's important to state here, otherwise we can't get the proof to go through in the recursive case. Okay, left untouched. So now I'll show you in HOL how this looks. So this, of course, is as much more a show of what HOL looks like rather than the proof itself. The proof, I hope, is not that exciting. But this is going to show you what HOL looks like. Okay, so you see that HOL has started. So this is the HOL window, and this is my editor. I'm in Emacs, and Emacs has a mode for HOL. So okay, I load some stuff, and then remember, this is how I define the source syntax. So what I'm doing here, I'm copying over snippets of standard ML code. So you can see I can write normal stuff like n is equal to 1 plus 2. And this is just a normal integer. This is ML code. This is nothing to do with the higher logic. I can write fun factorial. If n is equal to 0, then 1 else n times factorial of n minus 1. And this is completely inside ML only. Oh, you see, overflow. While, yeah, so, but then we have things like this. It's also an ML value. But you see, previously I said, okay, give me like this n is equal to 1 plus 2. Then it prints out, well, n is an integer. Well, if I say truth, that is a theorem that is just true, which is not the most interesting theorem. But let's say I do add left add distrib, if I remember correct. Yeah, so this is another theorem. This is a bit more interesting. It's over natural numbers. So it says you can distribute multiplication from the left side into over add. That's just a normal thing. And then, so just to show you that this can be really done like any kind of thing, I don't know, I can put these in a list, val x's. Now I have a list of theorems. I have a true, and then I have the other statement, and there's a list of theorems. And what can I do with these? I could take, okay, I can map something over them. I can map gsim over it. Gsim should flip them if they're equalities. So now I applied it, and you can see the difference between the original and the one below is that well, true, it didn't change because it's not inequality, but the other one is flipped. So what used to be the right-hand side is now the left-hand side. And I'm just writing ML code here. So, okay, there's a question. You mentioned before that HOL did not work with dependent types. Does that mean that M and N and so on are types that have type num rather than the value with types? So I don't know if you can see, it's the hover is very small, but yes, M is a number. Yes. Yeah, types are very simple. So I can show more sort of programming with this if you want. Okay, I'll remove that. Okay, here we have a theorem. I can say, well, give me the conclusion of it. And now what I like previously I had a theorem, now I have a term. And I can then do things like, okay, destroy for all. And now I have, I took that term and I destroyed it. So now I have one term which is without and one which is just the M. And if I had done something else like destroy exists, it would have said, no, it's not an exist. You can't do that. Or destroy, and then I can take the first of that and I get M, and now I can do, what's the type of that? Type of M, and I see it is a number. Number here means natural numbers. Yep. And the coloring here is just green is for bound and M is for free variables. And I mean, you can do all sorts of things with this. You can do spec all. Let's say I don't want to do that. I want to do spec qspec. I want to say 4, and then so now I can instantiate it. You know, but you can see my point here is that theorems and terms are just things in ML, and I can use any kind of ML programming on it. I can store them in references. I can stick them in exceptions, raise them as part of exceptions. I can do anything I want with them. But I can't create them other than through things that come from the internals of the system. Okay, and by the way, this also means that when you do things like this, this is actually ML code. Yes, that's the private thing I mentioned before. They are protected. Type, theorem, and term are protected ML types. When you do a data type definition, we can, for instance, distinct. This is a bit hidden now, I think, so I have to do it like that. So I'm asking the system, in this theory, can you give me the distinctness theorem for inst? And it will fetch it from the theory and say, well, okay, const is not the same as move, const is not the same as add, move is not the same as add, and that's the distinctness theorem. Similarly, you can fetch out the inst, the injectivity. Const and const simplifies this. What I want to mention about this data type is kind of interesting that in Coq, I believe, definitions of data types are very much part of the sort of core logic. While here, they're not. If we go back to the HOL Light kernel, we see that data types, you know, are quite complicated. How can you fit this in? But you can't. This is the implementation of definition of a new type. Of course, it uses a few other definitions, but what you have to provide is you have to prove that some predicate exists, and then it will define a type that is I mean that is with this predicate. Yeah, so that's what you do to define a type at the very lowest level. But any user of one of these will use a data type package that does this definition for you, and then presents it as if it is sort of, makes it seem as if it's all built in. And the data type package in all HOL provers is actually quite complicated. But of course, you don't need to worry about it having a soundness bug, because it's all built on top of a very simple primitive at the bottom. If it has some bug, it'll just fail to do the definition and just sort of fail with an exception rather than actually doing something unsound. Okay, so now we get to maybe more, we just do routine work now. So here we have an inductive relation defined. This is slightly old syntax. There's ways better to do it, but I'm just sticking to what I had from before. So here's the first rule. It says evaluating the literal expression always evaluates to n. So in the slides, I use this downwards arrow in Unicode, but here I didn't figure out how to do that. So I just used a normal prefix relation. Here's the case for variables. So variable s in environment n evaluates to v if you can do a lookup in a finite map. So s here is a finite map. No, n is a finite map. S is a name, and you get v. And for plus, you just recursively do x1 to v1 and x2 to v2, and then the result is v1 plus v2. And when you make this definition, you get an induction scheme, you get a cases theorem, and you get the rules theorem. The most interesting one is the induction theorem, which I'll get to in a moment. And here I define the target semantics. That it's exactly like on the slides, so nothing too exciting happening here. The compiler function is also exactly as on the slides. And now we get to the first proof. Oh, by the way, something you might have noticed. In Coq, it depends on which style of interface you use to it. I think there's multiple Coq IDE and Emacs modes and maybe Visual Studio Code. Anyway, you notice that I can actually go up and down here and everything is white. There's no sort of curtain going down or anything like that. So there's no sort of, it's very free for all here. So I can copy in this, and then I can go and copy in something else. And I don't need to copy the thing in the middle. It's really the responsibility of the user to make sure that it makes sense. So for instance, if I copy in this again and then look at the definition of steps, it'll say, oh, well, yes, I'm using step, but I'm using the old one. So yeah, it's flexible, and users get used to this very quickly and don't mind it. But yeah, you can shoot yourself in the foot. There was a question, this F lookup, where does it come from? Yes, it is from the library. There's a finite map library that I use because it's convenient. Yeah, so here we have compile function exactly as we have it. And here we have the first proof. Okay, let's start this proof. Oops, what did I do wrong? So here, if you see, my goal stack is currently, I have to prove this theorem. And what do I want to prove? I want to prove that if you take some steps, you step through x's, append with y's. Well, that's the same thing as doing first steps on x's and then with the resulting state, putting it into y's. And does anyone on Slack want to say what I should do? This should be a simple proof. Not on Slack, on the chat. I can show you the definition of steps. Steps is defined like this. It does pattern matching on the first list. Yeah, I want to do induction. That's correct. So I just say induct, and I will do induction. And I don't have to, I could write induct on x's, but this is not necessary because if I don't supply it, it's going to do induction on the first thing. So that's what I'm going to do. And then I have two goals. I have the base case. I have to prove it for the empty list, and I have to prove it for cons. And for cons, I get to assume that it's true. The inductive, I get to assume what I prove, but for the rest of the list, which is normal. And here I would just use sim, but that's too long to type, so I tend to go with GVS or GS or something like that. But this is just by simplification. I'm going to oh no, so this only simplifies. It doesn't know what steps is, so it managed to simplify this because it just it's in the background, like stateful simplifier knows that the definition of append, so that's easy. But now I need to give it also the definition of steps, and now it's going to use this rewrite, and this is going to turn into the state, in which case this is proved. So I'm going to send that in, and it proved it. And I'm going to do the same here to see what happens. My suspicion is that it'll simplify this to cons on the outside, so parentheses around that. Steps will simplify, and it will simplify so that this matches, and everything should go. And so it did. And this is how an expert user would write this proof, is to just write that. Don't care if it's two different goals. Just prove it for me. And so now I'm going to give this to the system as a theorem. And what I got out is, look, an ML value called theorem, or of type theorem. And I can use this wherever I can use a theorem. But actually, I wrote simp here because I want it to do the simplification wherever it can. So I don't have to mention this theorem at all. So for instance, this is another sort of, if we look at the type of this function, srule has this type, given a list of theorems, and oh no, I didn't mean srule, I meant scon. Scon. Oh, this is a bit annoying. It abbreviates it, but basically it has the type theorem list to term to theorem, and so I'm going to give it a list steps. I don't know. I'm going to do x's plus y's plus z's, and now without giving it any other information, I just say, okay, simplify it. Oh, it's did it not? Ah, I need a state. Okay, so you see the stateful simplifier, which is inside this scon, immediately applied this rewrite twice. It has x's on the inside, then y's, and then z's. So when using HOL, you really want to make everything about rewriting. The sort of yeah, that's how you make proofs, how you develop proofs quickly. Okay, so now I'm going to do the main proof here, and I need to be a bit wary of time. So, oops. So I don't know how familiar you are with induction theorems. So the induction theorem we will use is this one. This comes pretty much directly out of, I massaged it a bit here, but this is the induction theorem we will use, and it comes from the definition of eval, which is the source semantics. So it says to prove a goal like this, and notice P is a property, it's a variable, so it can be anything. To prove a statement like this, so what this really says, that if you have this as an assumption, to prove this, it suffices to prove the num case, the var case, and here we get to assume that, and the plus case. In the plus case, we get to assume for the arguments x1 and x2, p. You get to assume p for those. Okay, so now let's use that induction. Eval ind. And now we got a much bigger goal, but don't worry. Actually, I'll do a repeat strip tag. Okay, now we have 3 goals. So we have 3 goals. The first one is here. It's the num case. So if you look at this statement, it's exactly this statement, but with x set to num res. Then we have the var case, and then we have the big case for the last bit. Okay, so let's try to prove the first one. So I think Coq has this sort of bullet point stuff. So for sub goals, and so does HOL Four. It's not the same though, because this is just ML code. All these tactics are just ML code. So repeat just takes a tactic and makes a tactic out of it. Repeat strip tag is then a tactic, and this thing is also a tactic combinator. So it's then, oops, did I write it wrong like that? So it's a bit complicated, but it's a tactic and a tactic. So it composes 2 tactics, and so does this as well. So okay, but let's prove this one. How do you have any suggestions? Anyone on the chat have suggestions how to make progress in this proof? So we are in the num case. It should be simple because the compiler is simple, the semantics is simple here. Okay, I won't wait too long. Yeah, exactly. Try to simplify. We can use simple GVS. GVS is a fancier simplify, so I use it. So I didn't declare compile as a simp, so I'm going to do it. Just apply it. And now I also need to give it steps and step. And it was to this point simplified. So you see that it's quite aggressively simplifying. But now I need to get rid of this function update. It sort of, so it has proved this part that the result is correct, but it hasn't yet proved that that the last bit of our conclusion, that it didn't change anything underneath. So that we need to do. So to do that, I'm going to rewrite this to something. What's it called? Apply update theorem, I think. So this theorem I'm going to use. So if one of these updates is applied, then I can if. The style of making things around rewrites is I've seen argued for Coq too, adding them to rewrite bases with hint rewrite. Yeah. Good. Yeah. So that this tactic then proved the goal. So you can see that I don't have any curtain coming down here or anything like that, or waterfall or whatever you call it. I just have to manage the state myself. I can edit like anywhere. I can destroy my state of the buffer, but that. Anyway, and now for this one, I would say I'm going to attempt, just to see if I'm lucky, I'm going to run the same tactic for the next case. And what did it do? Oh, I might have done it wrong. It proved it. Okay. So the same worked on both. Okay, so now we only have the interesting one left. And here we need to be possibly a little bit more careful. I can still try it and see what happens. Oh, it looks pretty good actually. It did stuff. Maybe a little bit annoying is that it duplicated because it expanded the let. So since this works so well, I'm going to just keep that. And what I'm going to do is, this is now my proof. So it sort of swallowed the two first sub goals, and we're only left with one sub goal. And this is very common that you try to keep your tactic as linear as possible. So even though I had 3 cases, I might have had a short proof for the first 2, but then after that, so these ones pick off the first sub goal, and this one then continues with all the remaining sub goals. But what you try to do is you try to keep it as sort of as far indented to the left as possible. So and whenever you go into a sub goal, you have to indent one in, or you don't have to. You can write horribly formatted tactics. But the idea is that you do then ones on the early ones, and then you leave one that's the complicated one left. Okay, but here we are at the goal. So, okay, let's try to make some progress here. I'm looking at, I would like to get some kind of knowledge about this one. So I'm going to use this, my assumption, and which one? This inductive hypothesis, because then that gives me something about X applied to K. And the way to do this is the simple way that maybe beginners use is that they will take this and instantiate it to K and state. But a slightly more expert user will do this. Now, this one grabs the first one in the list. Well, last and first, but it is last because it's that's just the way it's counted. And then it derules, so it tries to match its assumption to an assumption in the goal, and this one will match, and so we will. And I have an X there so that it removes that because we don't want it around afterwards. Okay, so what did it do? It did what I said it should do. It took this assumption off. So now where we had X, it's now gone, but we instead only have left this X prime one. And instead what we have is we have extra stuff added to the goal, which we can, with a strip tag, get down from there. Okay, so this is what we got now from instantiating the first inductive hypothesis. Is we get that this is equal to res, and you can see we want to have res and res prime coming out of here, and this will simplify this one to. No, it doesn't simplify it. I don't think, because this is looking at the K part of it. Anyway, one can, just to make it readable, in this case, you can say, I want to abbreviate state 1, state maybe, so that's really obvious. So, and then GVS just sort of cleans it up. So now just for readability, I did this. I introduced the abbreviation state 1. We probably won't need anything about it, really, not much. Okay, and then we have the next one. And now again, I could possibly do some clever thing to sort of instantiate this automatically, but in this case, it would maybe be a little bit too clever. So I go with this. I say, okay, let's instantiate assumption 0 and QSpec. This is how one instantiates. I need to give the instantiation. K should be K plus 1, and state should be state 1. And then what should I do with it once I have it? I want to put it onto the goal. So that's what I did. Oh, could be a slightly wider. And I mean, I'm doing this quickly, but that's because I want to still have a little bit of time to show you other things. And then I have another goal here. It added this to the goal. I can go to impl tag that, and then I should. How do I do this? No. I see. I see. I might need to do something like this. Oh, maybe I'm not getting this right. So I know that I is less than k. So it should be, right? But why doesn't it do it? Do I have type issues? Oh, oh, okay. Surely simp should have got that. Yeah, fine. So now I'm going pretty fast, but what I want to get to is around the corner. Oh yeah, well, it's really around the corner. It's proved now. So yeah, what I did was I can take it at least in 2 steps. After instantiation, I found out that this is equal to res prime, and that will give me that this is equal to res prime, and then this one, thanks to this, is the same as state one, which if you then look up state one k, which already is the result you're looking for there, and then it managed to prove this also. So you can see the simplifier is pretty powerful if you set it up right. I was a bit surprised by this one being complicated. Yeah, so that was the proof done. And I still hope to have a bit of time to show other things, but I'll happily take questions here. If there's any questions. Just for... there are 2 more things I'd like to show you, and we are running out of time. So I could show you an operational semantics for a Haskell-like programming language, or I could show you n-bit word type in HOL. I think I want to try to have both. I'll show you the n-bit word type first. Oops. So you might think that I'm just opening libraries here. You might think that, oh, okay, if we can't have dependent types, that means like machine words will be a bit complicated, because surely if I want to write like 5 word, and then I say word 32, okay, how this 32, is it sort of, then I have to have a word size for 32 and separately for, like, you'd think maybe that this is somehow hard coded or can't be part of the type, because you surely want 64-bit words too, or I don't know, if you can write it like this, 58-bit words or 581 words. And this is all possible. And how can that be? If you don't have expressive enough types, and it's totally possible through a trick that's, I don't know if John Harrison is the originator of it, but he certainly wrote a paper that explained it very well. The idea is this. Yeah, so this works, by the way. So this, by the way, is a word literal 5, and this is just a word variable 5. But if I have 2 literals and I want to, I'm going to evaluate this, and I get 17. But I think if I make the word size small enough, it'll truncate it, right? Because the word size doesn't have so much space. Oh, I picked bad numbers. Okay, yeah. Oh, well, I could have picked better. Yeah, anyway, so it works. And the idea is this. In general, the term and type level are separated, unlike in COR. So term and type level can't communicate, except you can do something like this. You can ask, what's the cardinality of the universal set? That's always well defined. And for any, so a alpha set or sets are just predicates. So this is the cardinality of that set. But now, if we put unit here, that's of course 1. There's only one element in the set that, or there's in the universal set of all unit values. There's only one. How about Boolean? Well, well, why do I copy it in? But this, the cardinality of this is 2. So we managed to get numbers in, at least we can express some size stuff in the whole logic at the type level and get it at the term level. And so it only makes sense for finite things. So I can write bool plus bool, and that will be 4. The cardinality of this set will be 4, because and I can do +1 with option. So the cardinality of this will be 3 because there's none, there's some true and some false. Those are the options. So this is how you can. So if you have a type like that, it's actually, when you take it apart, it's not a number in the same way as these. It's just a way of encoding how large we want the representation to be. And the representation of Booleans, of words, is just, let's have some type, so some indexing type, and map that into bool. So because machine words are of Boolean type, and this is the indexing type, and then we pick elements from it to figure out where we're going. Anyway, that was maybe too quick to really understand it. My point, though, is that we can have different length words. So if we look at word add ASOC, for instance, I think that's all capitals. That's maybe not the best one. So here, if you now do conclusion and dest for all first and type off, we can see that the type of the first for all is an alpha word, so it works for any instantiation of type width, of word width. So it really is parametric or polymorphic, completely polymorphic in that. And finally, before we finish, I just want to show you one cute thing you can do in HOL. Eval, I think. So this, now I've just concentrate on the script part. We verified a compiler for a Haskell-like language, and this is the definition of the semantics, or a part of the definition of the semantics. So evaluation goes down to weak head normal forms, or weak head forms, yeah. So a weak head can be a constructor where we still have, instead of values at the sort of the payload of it, we have other expressions that if we then look at, we can then evaluate them to weak heads and so forth. So it can be a constructor, or it can be a closure, or in a function value with a name for a variable, and then expression of the body of the closure, atoms, errors, and divergence. So coming from a sort of Coq perspective, this one might be surprising, because we want a function that returns divergence when the operational semantics diverges. But how can a function return divergence? Okay, so that's what I want to show you in the last minute or so. So here we have a normal function that's defining how to evaluate the weak head for a given expression. But to make this actually work, we have it clocked. So we have evaluate weak head to a specific clock. So for instance, in the app case, what we do is we evaluate the first expression x with the same clock as we're given. And then if that timed out, so the clock ran out or the fuel ran out, then we return divergence and or timeout essentially. And then that is the result, divergence for the whole thing. Or if it's not, then, well, we're going to destroy the value we got. If it's a closure, then we do something. If it's not a closure, that's very bad. Something went wrong and we're erroring. It's a type error. So if we got a closure, then we have a variable and a body. And now we check, have we actually run out of fuel or clock? If so, then we say we ran out, we can't finish. And then otherwise we continue, we decrease the clock and we bind S to Y. This is call by name semantics. So we substitute the name S for Y in the body and then just continue evaluation. So yeah, that's how this semantics works. Now, what I want you to look at is the fact that we have a clock here, but that's kind of annoying. Shouldn't evaluating of the function be applied to consume fuel? Not necessarily. So I think many people think that clocked functions need to like decrease the clock on every recursive call, but that's just causing lots of pain, I think. What one should do is that the termination argument here is that so we can look at how the termination is. It's here. So the termination is a lexicographic product between the clock and the expression size. So in this case, the clock is unchanged. That means the expression size must go down. And indeed, here it goes down. It becomes only x from app. From app x, it shrinks down to just x. In this case, the expression size can increase because we've added stuff to it. And that's why we have to decrease the clock. Okay. But okay, so this is a clocked semantics, and maybe that doesn't surprise you. But what might surprise you is that we can define a non-clocked version. And the definition of it is as follows. It says, given an expression, I will evaluate it to a weak head. And the evaluation goes like this. There's a question, is there a clock for which it doesn't terminate? So is there some clock such that K does not terminate? If so, give me a clock that is such a clock. And then I will just evaluate it with the clocked version for that clock. Now, if it diverges for all clocks, then you get none here and we return divergence. This, I think, makes a lot of intuitive sense, right? So if you can't find a clock for which it terminates, then the result should be divergence. And this is a kind of silent divergence. So it has no result, like no visible output, which is consistent with Haskell. Anyway, so you might say, oh, well, this is pretty awful to work with because, you have this weirdo thing that asks about clock. Well, yes, it's not nice to work with, but we prove various lemmas. For instance, eval weak head app. We prove this as a consequence of that. So eval weak head of app unclocked is the same as evaluating x unclocked. If you get divergence from that, then it's divergence. Otherwise, we look at the closure. If it's not a closure, we error. Otherwise, we just evaluate the body with the substitution in it. And look, there's no clocks whatsoever here. We totally removed all clocks. No, so this semantics is call by name. It's not what's it called, call by need. And we chose that because we want to have much more flexibility in the meta theory. I'm not completely convinced Haskell is call by need, but I mean, I suspect one can at least make it not be that by telling it to inline things where it shouldn't, that kind of thing. So creating sharing that didn't exist originally, that kind of thing. Or breaking it, actually. Anyway, so that's what I wanted to show, and we're out of time. But I'm happy to take questions still.
Great, thank you, Magnus. I think it was really nice. It's shows very different aspects, and also compared to using dependent type languages like Coq and some variants. So Magnus, just I guess you're a little bit biased since you've been working with HOL most of your life, but any general thoughts about HOL 4 compared to Isabelle in terms of what you can and cannot do? I mean, are there some pros and cons there? And also if you can compare it to the dependent type like Coq or Lean, but just some general thoughts from your experience.
Sure. Okay. I remember once being asked what's the best prover, and my answer was something along these lines, that the best prover is as minimal and simple as HOL Light. It's as programmable as HOL 4. It has the the archive of formal proofs of Isabelle. It has the sort of PL coolness of Coq. It has the modernness of Lean. It has the user interface of Isabelle, and it's really a mixed bag. So so I think, but let's just compare HOL 4 and Isabelle HOL, just to make it simple. Isabelle HOL is much more engineered, let's say. It has type classes, it has locales, it has a nice user interface, nicer than this. It has more automation, it has Sledgehammer and so forth. And it has counterexample, like you type your lemma, and then it might just say, oh, but I can prove this is false, even before you start doing anything. So it's very fancy, but it also, because it's so sort of heavily engineered, it's also a bit more complicated, especially if you want to get under the hood and program it. So in that way, it's different. HOL is a bit simpler in many ways, not only in the sort of, it's simpler, but I'm happy with it. In terms of Coq and so forth, I mean, I've never used Coq properly, so I can't really say. But I have one of my PhD students went to work in Philippa Gardner's group, which uses Coq, and he was saying, but where is the simplifier? I so miss the whole simplifier. So I think rewriting and simplification is not as well supported in Coq, and that I understand, and I think it's inherent to type theory, because equality is more complicated in Coq.
Good, thank you. I don't think there is like a one best solution. But no. Rather it's a lot of history, and it's also what people are used to and so forth, because it takes time to learn one of the theorem provers. And
yeah, certainly.
Yeah. I think you have a question here also from...
Do you have any pointers to getting started with HOL? Sure. Well, like HOL 4, the best one is just to get on Discord. This is the website, and you can go on to Discord community. Yeah, so Discord there. click it, join it. It's really the CakeML project Discord, but it has a very active HOL channel, which is the place to ask both beginners and expert questions. And I mean, if you just want to sort of start, just read this. Go to GitHub. Yeah, here's I wrote the first version of this, how to just sort of set it up and like get going.
Okay, great. Thanks again, Magnus, for this very nice tutorial. And
it was a pleasure.
yeah. All right. So thanks again.